Hello, and welcome to ChemQuest number 10, Bohr's Atomic Model by Louisa. That would be me. Number 1. Consider swinging a rock on the end of a string in large circles. Even though you are constantly pulling on the string, the rock never collides with your hand. Why is this? Well, the rock must move so quickly that the pull from your hand isn't enough to pull the rock into your hand, and if you were to let it go, it would just fly away in a straight line. And also the pull from your hand keeps the rock close to you, but because of its initial velocity, it doesn't ever get close to you. Question number 2. Even though the Earth is attracted to the Sun by a very strong gravitational pull, what keeps the Earth from striking the Sun? I got a little nice picture going there. Yeah. Well, the answer to that is because the fact that the Earth is moving constantly keeps it from ever striking the Sun. And the Earth would move away from the Sun, but because of such strong gravitational pull, the Sun attracts the Earth. And that's also why the Earth has a circular orbit as well. Number 3. Why does the moon strike the Earth? Well, it's pretty much the same as questions 1, 2, because it has such a strong gravitational pull, the moon can't really go anywhere. It's just kind of stuck. So, hence why it orbits. Number 4. How could it be possible for electrons not to collapse into the nucleus? Well, the electrons must be moving in the orbits like ridiculously fast that the pull from the nucleus isn't enough to attract them towards the nucleus. And this is also known as Bohr's solar system model of the atom. And if you don't know what that is, look it up. Okay, we finished that part, and we have a little informational thing on light. So I would read that before answering the questions because you'll probably not know what to do. Just saying. Okay, we can start with number 5 now. As the frequency of light increases, what happens to the wavelength? Well, if you look at the picture that I put up, we can see that where the purple lines are, that's where the frequency is increased. That's also known as high frequency. And so when you have high frequency, you'll have short wavelength. So hence, the wavelengths get shorter. Wrong question. Oops, there we go. As the frequency of light increases, the wavelength gets smaller, and that's exactly what we talked about. And just like a little fun fact, well, you should know this, but the wavelengths must always equal 3 times 10 to the 8th power. Okay, number 6. What is the frequency of light that has a wavelength of 4.25 times 10 to the negative 8th? Yes, it's math, but honestly, it's really easy, and it's not hard, so you guys will be fine. Well, we know that C equals F times lambda, and if you didn't read the top section, C equals the speed of light, F equals frequency, and lambda equals wavelength. So if we convert that equation to equal frequency, well, to look for frequency equals C over lambda. So we just plug everything in. We know that C is always a constant. It's 3 times 10 to the 8th. That's what I said before. And then lambda, which is a wavelength they gave us in the question, was 4.25 times 10 to the negative 8th. Yeah, I forgot the negative. Sorry. And so we get an answer of 7.06 times 10 to the negative 7 hertz. And if you do the math for the units, the meters both cancel out. And so you get seconds to the negative first. And a little side note, it's the same thing as hertz, but you'll see hertz way more frequently. So you probably should just get in the habit of writing hertz and not seconds to the first. They're negative first. They're both the same, but hertz is just more commonly used.